Recording. All right, welcome. Oh, what happened to just okay. All right. Okay, guys. So we are going to practice a little bit of this ideal gas relationship, ideal gas quantities or parameters and the equation of states. All right. So this is the one. Look at this. It might look a little bit complicated because they put them all in one line. However, if you only focus on the first pair, that's the P right there. That's the V right here. That is the temperature right there and the numbers of molecules or atoms in the system. That's it. That is a structure of the equation. P times V equal to nRT. That's how they arrange them. And once again, there is another common way that you can quantify the amount of gas in the system by using the capital N. That is simply just the numbers. So the small n, we represent the n, the amount in mole. The capital N is just a pure number. That's the difference, okay? But the structures of the equation look the same. If you use the mole, you couple with a constant R. That R is called gas constant right here. But if you decided to use the pure number, you just couple that with another constant called Boltzmann constant. All right, but the structure of the equation are exactly the same. PV is on the left, temperature is on the right, and something in the middle give you the amount. Okay, and the constant, you just have to choose the constant according to the unit of the amounts that you use. Sounds good? All right, so simple enough. This equation called equation of state because it tells you the state of this gas. Anywhere in the universe, no matter this gas shows up any corner of the universe, it has to follow this simple equation. This is one of the very amazing facts. And that is because everything is still sort of like has the same physics. So it still has to follow this rule somehow. So this is kind of nice. Okay, one comment though, don't forget the temperature here that you are using, you always have to use absolute scale in this equation. You cannot use Celsius scale here. So everything that shows up in this equation must be in Kelvin. Sounds good? All right, you have to convert them into Kelvin before you can use this one. So one consequence of this is nice. Because if you move whatever on the right and just bring in the temperature, the right-hand side, it will be either number of moles times R or the numbers of particles times Boltzmann constant. The right-hand side are constants anyway. All right, so as long as you have the fixed amount of gas, do not leak it out, there's no adding stuff more, the PV over T must be fixed. That's why you have this simple relationship that you can compare between the different states of gas. Okay, you can use P1, V1 over T1 equal to P2, V2 over T2, on and on and on. Okay, so this is nice. So what it means is gas will behave according to this relationship all the time. If you try to increase some, decrease there, the third quantities has to follow this equation. It cannot get out of this. Okay, so this is kind of like, at least we know the behavior of gas really well. So that's why this is a reason that we pick ideal gas to be the system that we're going to use as our studying material for thermodynamics. Sounds good? All right, we have a very concrete equation that allow you to know the state of the gas at all times. So that's nice, very nice. Okay, so with this, let me practice how this can be used. First, for example, Mojan, you have an ideal gas, you have the volume, you have the temperature, you have the pressure. All right, now you can see some of them is already in good units, some of them are not good, but we have to convert them anyway. Determine the number of mole. That's what they want. So this one is a small n. And the total number of molecules, this is the capital N. Everyone good? All right, so this is just the two different units that you use to quantify the amounts. So let's start with the small n. So you bảo John, okay, use PV equal to small n RT. Here you go. And that's how you can figure out the number of moles by taking the PV divided by RT. Nice. Now, the only problem that might show up is the units. You have to use the SI unit. So look at the pressure first, guys. Pressure is right here. It's in Pascal already. We love it. It's SI system. So let me put 10, 1, 2, 3, 4, 5, 10 to the 5th Pascal. So that's checked. What about volume? The volume is not yet. It's still cubic centimeter. So you must convert that into cubic meter. You multiply by 10 to the negative 6. Everyone good? So I just do the unit conversion from cubic centimeter to cubic meter. Now, what about temperature? Oh, underneath the temperature is, all right, R is R, just leave it there. And the temperature is in Celsius. That's not good. You want it to be in Kelvin. So you do 20 plus 273, turn it into Kelvin scale. So everyone good? All right, so this is how you use this equation of states, making sure that you use the SI system for everything to properly be calculated. And this is one thing that you can always do in the exam. You don't have to substitute the R. I think R is there, is good, it's nice and clean. So it saves you sometimes for the calculation as well. So I personally love to just leave it as R right there. It's fine. Okay, it's cleaner. And then you just work around the R numbers. All right, same thing will happen if you were to calculate the capital N, the total numbers of molecules. You just use another constant, which is called Boltzmann constant. But now you can see everything will look exactly the same, except you just switch the constant. Sounds good? All right. So, well, but you can expect, I think mole is just another unit that we are going to use a lot. Because who would want to just keep talking about like, hey, I have like a million molecules in the system, you know? It's just easier for just say, hey, I have 2 moles of gas. We call it done, right? So the small n is more popular, I would say, right? It doesn't make any sense to just keep using the capital N. The number is huge. It's just hard for you to imagine. All right, so mole is going to be our major unit that we're going to use a lot more than just the just the regular numbers, capital N. All right, guys, try again. At least you get a sense of what is happening for the gas. One more, it could be like this. Pure helium gas is admitted into a tank containing a moving piston. The initial volume, pressure, and temperature of gas are given. That's good. That's good. All right, so you get complete sets of all the P, the V, and the T. Now, the volume is decreased, the pressure is increased, find out the final temperature. You see how it goes? This is what happening is when you want to go from one state to another state by manipulating those quantities, this is what happening in gaseous system that can be easily calculated using this relationship right here. Right? Because it has to follow this fixed sort of like relationship all the time. So you can just use that here. So let me name the condition number 1 to be anything related to 1 with the subscript 1. And after the change, you get a new volume, new pressure. You want to figure out the new temperature. Let me call it the condition number 2. And use that relationship. You say P1 V1 over T1 must be equal to P2 V2 over T2. Yeah. All right. And because you just want to compare left and right. So in this time, making sure that, well, you just use the right unit, but on both sides, that's good enough. For example, pressure. P1 is in kilopascal, 200 kilopascal. So you don't have to convert it into anything as long as the right-hand side is also in kilopascal. Does that make sense? All right, so that saves you a little bit of time. Don't need to convert all the units. So making sure left and right are coherent, everything is good. So volume, it's in cubic meter. All right, 15 times 10 to the negative 3 cubic meter divided by, the only thing that is sort of like annoying is temperature. You cannot use Celsius whatsoever, right? You have to use Kelvin all the time. So this one is already given in Kelvin, so this is good. Put it there. Now you equate this to the right-hand side. Now P2, it's already in kilopascal, so that number is good. 350 kilopascal, all right? Both sides of units are good. Volume is also in cubic meter, so that's also good. So we can just use that number there. There you go. 10 times 10 to the negative 3 cubic meter. Perfect. Divided by now the temperature of the new condition. Done. That's how you calculate the temperature after the adjustment. And the answer will be in Kelvin. Good, good. All right. So not bad, not bad. This is pretty reasonable. You can calculate this thing. All right. So with this, we have a system, which is gaseous system, that we're going to use it in our thermodynamics study. But before we get to that, it turns out next time you're going to see that there are components that comes to sort of like build a law in thermodynamics. And today we are going to propose the first one. And that one is heat. All right, guys. Okay, okay. All right. That's the first component. All right. And I would like to start this concept of heat by asking you, how do you feel about this word? Heat energy. How do you like this one? That sounds all right. Yes or no? Heat energy. Is it good? Maybe. All right. But once you're done with this course, you have to make sure that you don't use this combination of words anywhere, anytime in your life. This is illegal. It could be against Parabol, whatever things that you นำเข้าข้อมูลอันเป็นเท็จ or whatever. This is not good. All right. Heat energy is not good and is illegal. The reason it is illegal because, here we go, guys. The definition of heat is energy transfer. Heat is energy transfer. Heat is energy transferred. Heat is energy transferred. Seriously, heat is energy transferred. All right, if you don't get anything today, this is the only thing that you need to get. Heat is energy transferred. So that's why this word doesn't make any sense, because it's the energy of energy transfer, right? What is it? Like, it's a heat energy, the energy of the energy transfer. So what I'm saying is, heat is already include energy in itself. So that's why the unit of heat is going to be in joules. No question asked. It's energy already. However, we use heat to signify that there is a transfer mechanism built in. So that is the dynamics that you are looking for. You guys with me? All right. So heat is showing something is flowing. Energy is flow from one place to another place. There is a transfer going on. There is a transaction going on. So that's why, Bojan, if you want to talk about the energy that is inside the body of the system that we have been talking in the morning, what is it? You're going to have to use the word thermal energy. You guys with me with this? All right. The thermal energy, that is the energy in your system based on the temperature level that you have. So at this point, your body temperature is 37 degrees Celsius. That's, you have some energy in yourself. You have thermal energy in it. However, because your body is hotter than the environment, you are losing energy all the time right now, right? You have some body heat leaking out. That's why it's a transfer. Your energy from the body is coming out into the room. That's why we call it the heat, because it's a transfer. Good? All right. So that is the distinguish between thermal energy and the heat. Heat is a transaction that needs some movement. Something is going on. Okay. Before we move on to the real stuff, there is another thing that comes into play from time to time. Historically, we didn't have joules units before. We study water, so that's why there is another unit that's still sort of like currently used today is called calorie. Okay, so there is a conversion between the two. If you see calorie, 1 calorie is 4.2 joules. Okay, however, it may be a little bit more even confusing when you see calorie in food packaging, right? When you look at the label, it says that there is a 230 calories if you eat this, whatever, 8 grams of stuff, and then another cup of this. This is a big cow right here. The C over here is a capital C. So food calorie is 1,000 hour calorie. Okay. All right. So in the European food packaging, they are more scientific somehow, I can guess. They give you in kilojoules and also in kilocal, just a regular one. So I think they are more scientific, sort of like minded than the rest of the world, I guess. I don't know. All right. But some level is very good. They give you exact energy in the, well, conventional units, I think. All right. But anyway, that's a good thing. You can convert between just the regular calorie, a big cow, the food calorie, or the joules, right? They just convert back and forth, all right? But for us, we stick with the joules. We stick with the joules. Okay, here we go. So what is going on here, guys? The point that we want to make here is the last stop of the day is this. So now we understand the temperature is the level of energy of the system. Heat is the energy transfer. So now there must be something is going on. So I would like to present to you this stuff right here. This is fun doing together. Guys, if you have a particle, just a single particle, monatomic gas or anything, electron, proton, neutron, doesn't matter. And then I give this some energy. Maybe I light the fire, shining the laser beam on it, doesn't matter. What do you think it will happen to this particle? You give it some energy. This particle has to do something with that energy, right? What can it do? There's nothing else can it do. It just move. It has to move. Because once this particle gains some energy, it has to do something with that energy. But because it has no internal structure, the only way that it can express the energy is kinetic energy. It just have to move. All right, make sense? All right, okay, that's good. Because we said when it's not moving, it's at 0 Kelvin, absolute 0. So once it gains some energy, it has to travel somehow to showcase that, hey, I have some energy in me. But because I have no other choices, I have to move. Now let's contrast this to another molecule. Let me upgrade this into a diatomic molecule. And let's say I give this molecule the same amount of energy. What should these diatomic molecules do now? Well, John, it has to move. Doesn't matter. But now it has some internal structure. With me, guys? So it can rotate. Wow. All right, from 101. There is a rotational kinetic energy associated with the rotation all the time. So in this particular shape, you have a rotational kinetic energy built into it. But of course, rotation doesn't move anything. It just sort of like a wiggle left and right, up and down, doesn't matter. It doesn't travel. So it's a different kind of kinetic energy. Okay. But wait a second, Dan. To be realistic, there's no diatomic molecule that is so rigid in structure like that. Why don't you put some elasticity into this diatomic molecule to reflect maybe Van der Waals force, maybe I don't know, covalent bond or whatever. It has some, oscillations and things that it's possible. Yeah. So if I give this the same amount of energy again, what should happen to this? Well, of course, it still be able to move. It still be able to rotate. No big deal. But now you can see that there is a possibility of vibrating back and forth, simple harmonic motion. Yeah. So there must be a vibrational kinetic energy. Okay, got an idea? All right, so I'm just doing a comparison between these three scenarios. A simple structure, a diatomic, but with the rigid structure, and the third one with a little bit of flexibility. My question is this: which one should move the quickest? The leftmost, the middle one, or the rightmost? So now think of it, because the left one, you have no other choices. All of the energy is being used as a translation of kinetic energy. So the answer will be, Ajahn, of course, the first one, because all the energy being used to translate. Make sense? But on the rightmost, you have so many choices to store the energy. It could be rotation, it could be vibration. So only partial of the energy being used for translation. So it's going to move a little less. Sounds good? But now you said, Rajan, wait a second, you already said the translational kinetic energy translate into temperature. You got it? So if I change my questions, which particle should raise in temperature the most? It will be the left one, the first one again. You guys with me? Yeah. This things that I'm trying to explain over here, this is called heat capacity. Everyone with me? Got it? When you have many ways to store energy, you have high capacity, because there's so many techniques that you can, gather your energy with you. But if you have a very simple structure, you have no other ways. Once you get the energy, I have to move. I have nothing else to do. Okay, make sense? So the ability for you to raise the temperature relying on how big is your capacity. If the capacity is big, the temperature will raise a little. If the capacity is small, like the left one, the first one, then the temperature will raise a lot. Sounds good? So now I can make a connection right now. If you have this energy transfer into this one, guys, this is it. This, you call it the heat. Isn't that nice? Energy transfer. Yeah, I transfer the energy to this molecule. Yeah, but then because this has to connect with ability to store energy, let me name it C, the heat capacity. But this will reflect in temperature change. The bigger the C, the smaller the temperature change. The smaller the C, the bigger the delta T. Make sense? It's a product between the two. Okay? But no matter what, once you multiply these two together, it must be the same as the amount of energy get transferred to it. Okay, cool. But then we're not going to do this all the time, Ajahn. If you do this C all the time, every system will have its own C. It's going to be kind of like a lot of work to do. I'm going to transfer this into mass times mini C. This one we call specific heat. It just heat capacity per kilogram. So in the future, you have water, you can bring in 1 kilogram, 100 kilogram, 1,000 kilogram, doesn't matter. It's all water anyway. They must have the same specific heat. Make sense? It's a property of that substance. So make it a lot easier for you to deal with. And this give you an idea of this equation right here. Everyone understand this one? Heat is just the capacity times the temperature change. But to make it more convenient, we would love to do the amount of mass times the specific heat, which is the capacity per kilogram, and then multiply by delta T. You probably have seen this somewhere in whatever, maybe science or physics or chemistry, MC delta T. But now we understand a little bit better that it's just the energy transfer. Sounds good? All right. So this is happening when the temperature is changing. However, there might be a location where, a location means the temperature where things are not changing in temperature at all. We call it the phase transition. Everyone knows solid will turn into liquid sometimes, and then liquid can turn into vapor at some point. Yeah. Those transition period, we call it the phase transition or the phase change. And during that phase transition, there will be no temperature change. Temperature won't change. So that's why during this phase transition, you don't need to do the delta T. You only care about how much energy is needed for you to do that transition. We call this the latent heat. Okay, it's a hidden heat because it's hidden from the delta T. It doesn't change the temperature. So I can just use that here. How many kilogram of the material you're using, and it's during the phase transition, you multiply it by the latent heat. Sounds good? All right, so this one has a name associated with the change of the phase. If you go from solid to liquid, it's called heat of fusion. But if you do the reverse, we call the heat of solidification. These two are not very common though, I think. But the one that you're familiar with must be this. When you go liquid to gas, it's a vaporization. When you go from gas back to liquid, it's called condensation. All right, that's kind of okay. This is more kind of like familiar terms. Okay, so in conclusion, whenever you do the heat transfer, there are two things that is possible. It might be temperature change if there's no phase transition involved. You use Q equal to MC delta T. Or if you accidentally hit the phase transition temperature, yeah, you just take the amount of material multiplied by the latent heat. Sounds good? All right. So what can we do with this, guys? Before we move on, let's do a simple question just to check that you understand this concept. At the beach, water or sand has the higher specific heat? Water or sand has a higher specific heat? 1,000 points. What do you think? Water or sand has a higher specific heat? Sand, okay, all right, okay, okay. When you go to the beach during the daytime at noon, which one feel hotter to your feet? Is it sand hotter or water is hotter? The what? Sand or water? Sand, right? You feel that sand is kind of hot, water is kind of cold, yeah, when you run into the water. And that must be the indicator that is water has a higher specific heat. Does that make sense? Because it can store a lot of energy in itself, so you won't see the temperature raise that much. But the sand has a small specific heat, so it has nothing to do. It's just temperature just keep rising. Just think of the capacities like your stomach. Your stomach is small, so you get full very easily, right? When you eat a little bit, I'm full already. But if you have a big stomach, you can eat a lot. I don't feel anything. Just keep feeding me with more energy, more food. I'm good. Yeah, got it? So water has a higher specific heat than sand. But logically, that makes sense because sand is a solid. The structure is rigid. It doesn't have a lot of ways that it can store energy. But water is like liquid, there's a hydrogen bond, there's, Van der Waals stuff. So there's so many ways that water can store energy. Make sense? All right, so that's a good idea. Let's do some calculation. So the way that this thing can go is, okay, you have a temperature of silver bar raised by 10 degrees Celsius. So that is your delta T, that's obvious. And it's absorbed energy, that's your Q. The mass of the bar, that's M. Determine the specific heat of silver, that is the C. Done? Yeah, got it? So this is how you can calculate the C by using Q equal to MC delta T. Okay, and then that's it. The C is simply Q over M delta T. All right, making sure that you use the right unit though. So the heat is 1.24 kilo. You can put 10 to the third here. Mass is in gram, turn it into kilogram, no big deal. And delta T doesn't matter, is in Celsius or in Kelvin, they are the same. So I can use 10 degrees Celsius here. And your job is done. Sounds good? All right, so that is a simple way of using this MC delta T thing. It links between the heat flow, the mass, the specific heat, and the change in the temperature. Simply used. All right, so that's nice. That's nice. So what should we do today? All right, so the last exercise of the day is this. All right, so this one, well, put it as a DIY at this point because this is just like kind of general questions. what I really want you to learn today is a wrap up of what we have been doing today. We learn about temperature. We learn about the property of materials. We learn about heat is energy transfer. So this is one application of it. Here we go, guys. So everyone knows things will go from solid to liquid to gas, yeah? So if you try to trace the temperature change, of course, it will go from super duper cold, temperature rise to 0, melt, rise as a liquid water until it reach 100 degree and vaporize. Yeah. So everyone kind of like, okay, I understand this. But what can we do if we put everything that we learned today together like this, guys? If I have two parts of the system, one part is hot, one part is cold. All right, everyone with me slowly. So on the left-hand side, this is the high temperature. On the right-hand side, this is a low temperature part. And then you put them in thermal contact. You understand that they touch them. And because of the temperature difference, everyone knows heat flow from hot to cold all the time. So there is a flow of energy. Here we go. You start to see the thermodynamics now, about to. But then there must be heat leaving the hot side and enter the cold side. Yeah. But from the conservation of energy, these two amounts of heat must be the same. The amount of Q hot must be exactly the same as the amount of Q cold. Yes. But now, Bajan, wait a second. One is leaving, one is receiving. We must have a way that we can tell the direction of the flow. So this is what we're going to do. Anytime that you have a system, and if there's a heat flow in, you're going to call it a positive heat flow. And if the heat leave the system, you call it the negative heat flow. Okay. All right. So now we know the direction. So once you define the direction, I can get rid of that absolute sign and turn this into a proper mathematical equation that equate the two. Everyone good? So that's why you get this equation right here. You can put the negative sign in front of either one of those. Is the same equation anyway. So I'm just saying that if you have a Q hot, which is heat leave the system, it must be the same as the one that get received on the other end, but you have to put the negative sign in it to flip the direction for you to manage the magnitude. Okay, sounds good? All right, so this is the key point. You start to see the dynamics right now. Heat in equal to heat out. Heat cold equal to heat hot. That's simple. What can we use this for? Right here, guys, last exercise of the day. It's a very simple scenario. You do this all the time. You put ice in a cup of water. You just want to drink an ice water. That's all. Okay. So over here, you have a container that contains 200 grams of water at 50 degrees Celsius. Okay, very good. And now you have 500 grams of ice that you want to dump into this. 500 grams. There you go. Yeah, simple scenario. Okay. And of course, ice, this is just a regular ice. So it's going to be at 0 degrees Celsius for sure. Question is simple. What happened to this cup of ice water? What is the final temperature? Okay. I don't know, have you done this before? But if not, this is going to be a very good starting exercise for our thermodynamics journey here. All right. This actual scenario translated into this diagram that we just drew. Here we go. The hot one, T hot. The cold one, this is T cold. And this is ice. The hot one, this is water. Make sense? All right. And when you dump ice into the water, you just make thermal contacts. So there must be heat that flow from water to ice. Make sense? Okay. Ice receives some energy from the water. Okay. So that means there must be heat flowing out from the warm water and start melting the ice. So ice will start melting and warm up. Make sense? Okay. So that's why, all right, John, I can see it. That's a Q hot over here. and that's a Q code coming in. But then for you to be able to look at the grand scale of the temperature, let me overlay on top with this. Let me do this. Let me put 50 degrees Celsius on the right. Let me put 0 degree on the left, just like a temperature scale. Okay. And you know that it's going to end at some point. So let me mark the final temperature to be at X degrees Celsius, shall we? All right. So let's assume that is your final temperature. Okay. One thing that will happen is water will cool down. Everyone good? From 50 to X. Okay. That's a cooling down of water. But because this is just a simple cooling down, there's no phase transition, you know you're going to use Q equal to MC delta T expression, yeah, to calculate the amount of heat flow. Sounds good? Yeah. But now look at the ice side. Well, okay, John, ice somehow has to melt first. So if ice need to melt, so let me expand that 0 degrees Celsius out a little bit. There must be the process of melting first. So ice must melt here. Got it? So let me put ML right here. That is the phase transition. It has to melt first. Once it melts, now you are down with the liquid water. Then the liquid water at 0 start to warm up to X. So from that point, you warm up using the MC delta T expression to the X degrees Celsius final temperature. Sounds good? So this is a thing that is gonna sort of like you combine the thermal contact, the concept of the heat flow, the energy transfer, and the amount to the temperature change based on your heat capacity. So it kind of like come into the full picture over here. But then because we know whatever that's cooled down must be the same as the one that warmed up. So what I can conclude is this. All right, guys. So the equation look like this. Mass of the ice times the L from the melting of the ice must be, or with mass of the ice is still the same mass. But now it's raising in temperature, C of water, delta T, final temperature minus initial. Everyone with me at this point? Got it, right? Ice melt, it needs M times L energy. And then ice, after has been completely melted, has to warm up from 0 to X. So that's an MC delta T. That's what it is. Okay, this is the warming up part from the TCO. Now, look on the right side. It's going to be mass of the water. Let me put the W subscript there. C of the water. And the temperature go from 50 down to X. So it's going to be X minus 50. Everyone good? Yeah. But now I know that these two must be the same amount. So the way that I do is I equate them with a negative sign in the front. Everyone with me? Got it? All right. And now you understand why I need an extra negative sign, because X minus 50 is always negative. The final temperature X must be lower than 50 for sure. So that parenthesis always give you a negative number. So if you want to equate the left side to the right side, you need extra negative sign, right? You want to compare the magnitude of the change. Sounds good? All right. But the reason I do this, because I want to stick with the delta. The concept of the change is the final minus initial all the time. All right. We want to keep that order of subtraction proper at all time. All right. So with this, your job is almost done, guys. So let me substitute numbers for you. M of ice, 0.5 kilogram. The latent heat of fusion, all right, I can go back and take a look at this. Water, here, latent heat of fusion is about 3.33 times 10 to the 5th. 3.33 times 10 to the 5th. What is the unit here? Joules. All right, very good. There you go. Perfect. So let me omit the unit here. Plus the same amount of mass is still 0.5 kilogram, unchanged. And then I multiply by the specific heat of water. Go back. Specific heat of water is right here. But don't worry, in the exam, everything will be given, so you don't have to worry about it. But let me read it out. It's about 4,200 approximately. So let me put it there, 4,200, and then X. There you go. That's the left-hand side of the equation. All right, and then you equate this to the negative of the mass of the water, 200 gram, 0.2 kilogram. The specific heat of water is still 2,200, same. And then X minus 50. Here we go. And from this point, you can evaluate X and your job is done. Everyone good? All right. So that is how you apply the stuff that we learned today. So this is the crucial main examples that we're going to use as a starting point of thermodynamics next time. But we only half done, guys. This is half of the story. This is heat. Next time, we're going to do the other half of this. And once we get that half done, we start doing the thermodynamics. Okay? This is not yet. Not yet. All right, guys. Before we wrap this up, I really want you to punch the calculator for this. I mean, later when you do the study, it turns out X is negative. This equation will give you a negative X. Yeah. What does it mean? What do you think? What does it mean? Of course, there's no way that you're going to have a negative X as your final answer, right? That's not possible for you to dump an ice and then everything going lower than 0. So the answer for this one is ice is not completely melted. Does that make sense? It kind of makes sense. Think about it. You have only 200 grams of water, น้ำ2 ขีด. You dump half a kilogram of ice into it, right? You're not going to be able to warm up the water. Does that make sense? It's only 200 grams of ice, and it's just kind of warm water, 50 degrees Celsius. It's not super hot. So in the end, when X is negative, it just means this equation assumes that you completely melt the ice. And all the energy go from the water. I mean, comes from water. You extract energy from water to melt the ice. But it turns out it's too much. The water does not have that much energy for you to melt the ice. Does that make sense? So that's why X is negative. So it turns out this problem, your answer is 0 degrees Celsius. That's your final answer. So it means only part of the ice gets melted. You guys with me? You're not completely melt the ice. You only partially melt ice. Yeah. All right, think about it. All right, but that doesn't make any sense if X is negative anyway. So something must be kind of off. So the reason is ice is still there. So your final answer is still 0. So you get ice water. I mean, that's just normal one. You dump a lot of ice into a cup of water, you get ice water. Yeah. Okay, sounds good. All right, guys, thank you. I'll see you on Thursday and I will bring along the exam. I'm sorry. All right, but I'll set extra time for you to take a look at the exam and then you can have questions then. All right, guys, see ya.